member in our computer science and engineering school. And we're very proud that he managed to get a real engineer. A real electrical engineer who was actually highly desired by essentially every university in Israel.
Thank you. Salam Ami. The workshop is machine learning for security, or vision and machine learning. Down to something very, very, very basic statistics for small security. I'm going to talk about covariance estimation, which I'm sure everybody here knows, unlike the rest of the stuff.
Don't assume anything like this.
Yeah. And I'm going to talk about two things, which will make it a bit different: large scale, when things become very big, and robust, when we want to be robust to outliers, to heavy tail distribution, stuff like that. And that's very much related to anomaly detection, which everybody's been talking about here today. So I'm going to give some background, remind us what is covariance, talk about the two issues that I'm going to combine, that's robustness and regularization. I'm going to start off by something very simple, a simple regularization that people have done before us, but didn't really understand why it works, and we're going to prove it. And then but we'll still see that it's not complete, and then we'll try to give a unified framework that makes it more clear and understandable. And then we'll hopefully not have time for discussion due to time constraints.
You're not going to do all the 50 minutes.
What?
Go ahead.
Yeah, okay. I have 40 minutes, right? Yeah. Okay. So the first two things, I guess, everybody learns in statistics are second-order statistics, the mean and the covariance. The mean is the most trivial, and covariance is a bit more, okay? Tells you how things are correlated somehow in a linear manner. It's like statistically independent in a linear manner. So it's very simple, very intuitive. When we talk about things, everybody uses the word correlation. In the Gaussian case, it is sufficient. It gives you all the information you need, okay? And algorithms which will be based on this statistics will be optimal. And alternatively, if you don't want to think about Gaussian, you can just say if I restrict myself to linear methods, techniques, or quadratic, usually these things are also sufficient and optimal. Now I'm going to give you 3 examples which I looked hard for in the case of security. Now these are really things that we are working on. So here's this is in Berkeley lab. This is a sensor network that they did in one of their laboratories. This is designed. You've got the 50 little sensors, most, that sense the environment. They measure temperature, humidity, light, stuff like that, and they're trying to monitor what's going on.
Sure. Is there any?
These things are very, very simple, very basic. They can't do all the fancy stuff that you guys are working on. Okay, basically what they cannot do anything more expensive than just to measure, let's say, their mean and correlation with the other sensors. And you use linear estimators to try to predict what's going to happen next, estimate which sensors are, what the temperature in some place, or even detect an anomaly or something like that. And on the right there, you see different curves of performance, which all depend on, you see all the linear estimator on the bottom there. You'll learn in the second year of, in your case, computer science, in my case, engineering. What you need is the input.
This is what we usually call the conditional covariance.
This is what you call the conditional covariance. Okay.
And this is precisely what comes from this Gaussian button explanation. CCA is diagonalizing this matrix.
I agree. So, and what you need to know, you got your measurement X, and in order to apply this estimator, you need the covariance. Usually we learn the covariance from the data. I mean, in class when we learn it, you give the students the covariance. In practice, we need to learn it, and that's basically what we're going to talk about. Another example, intruder detection. Again, this is all stuff that we work on with real-world data. Again, a sensor network. You put it in a room trying to detect when people come in and out. We use the most simple thing there is, an energy detector, something like that. It just measures the energy. When the energy goes up some threshold, we say there's an intruder, and we try to maximize the detection for a given false alarm rate. Again, these simple tests, all they needed, they take the measurements X, and you see in this case they multiply them by the inverse covariance, which they learned from before. Another example, here is the United States, the Internet 2 backbone network, the Abelian network. You observe the traffic on the links here, and you're trying to detect anomalies in the data here. One of the anomalies are, I won't go into the details, but they're in some kind of hidden subspace. And the classical thing to do here is PCA, which basically takes, again, your measurement X and projects them on the principal subspace. In this case, let's say the first eigenvector. Again, it's a function of the covariance, which we learned from some other data. And of course, whenever this test exceeds some threshold, we ring some bell. Okay, so in all of these questions, you needed to estimate the covariance from data. Okay, you don't usually know it. The basic problem is very simple. You've got a vector X of dimension P. Okay, and estimating the mean is very, very easy. So we'll just assume we know it and it's 0. And the covariance sigma is just defined as the expectation over X times X transpose. We've got get n independent and identically distributed realizations of X. And using them, we want to build a function, an estimator of sigma that will be close to the real sigma in some sense. And this problem becomes difficult, and that's what we're going to talk in two cases, which is exactly the title of our talk. One is when the data is non-Gaussian, and this can be because the data is just heavy-tailed and has a different distribution of Gaussian. Or it can really be Gaussian, but you've got outliers. Okay, you've got anomalies inside. You're in an unsupervised anomaly detection scenario. So in your training set, you also have anomalies. And these are the outliers. So 2 questions that everybody asks me before why I even do research on this. So the first one, is it even possible? And I think I missed. And the second thing here is that the problem is very easy when you have lots of samples and the dimension P is small. But in practice, today there are many problems when this is not right and may be of the same order as P. And today even people talk about the large P small n problem where n is smaller. Yeah? You've got less samples than your dimension. And think about the covariance of a p-dimensional vector as p squared, about half p squared parameters. So you need n to be very, very big in order to estimate them accurately. So 2 questions that people usually ask is, first of all, is this even possible? Can you really estimate a large matrix, lots of parameters with only a few samples? And the answer is, of course, generally no. But in practice, I think the answer is usually yes in many things. And the reason is, the first one is that we're not really interested in all of the elements of the covariance, okay? Well, we're going to use this covariance. This is just a first step for another goal, okay? And if we focus on the other goal, then we might be more successful. And the second of all is that in practice, at least in engineering, we usually build a system, and we have some additional prior knowledge that we know on the data, and we can take it into account. And we have that in all of the examples we showed. Like in this example, you see we know the topology of the sensors. And the different curves here are different estimators that take into account the topology, the fact that some sensors are close to the others and others are not. And we can take this into account. In this example where we talk about space, we somehow assume for some reason that there are hidden variables, and therefore the covariance is going to be low rank. And if we take all of these into account, then suddenly it does make sense to, because we basically have less parameters. We don't really need to estimate all of these. So that's the first question. And the second question that usually bothers machine learning people is then why do it in 2 steps? Why first use the linear regression, the standard least square solution, and then plug into the covariance into it? Why not just design an estimator from the beginning to be best for your goal? And the questions to this, I think the first answer is just a matter of taste. Second, you can see that usually if you take these two philosophies, in most cases you get to the same solution. So I really think it's a matter of taste. I think it's more natural to impose a structure and power knowledge usually on the covariance and not on your high-end goal. Because like when you look at the rooms there in Berkeley, you can really see which ones are correlated. And correlation has a lot of intuition to us. And modular design, which is when you can just use it as a black box in different algorithms, and every time all you need to change is the black box instead of changing the whole algorithm. And in this sense, it's better. Okay, so the most famous solution to this problem is the sample covariance, which is, I guess, what everyone here would do if you had this problem. Just take your measurements, xi, multiply it by themselves, and take the mean. Now, if xi are Gaussian, and if you've got lots of realizations and small dimensions, this is the best thing you can probably do. Sorry. This corresponds to maximum likelihood, asymptotically unbiased, asymptotically minimizes the mean squared error. Bless you. It's simple, no parameter tuning, basically everything we can hope for. Unfortunately, if you don't have these two assumptions, the sample covariance is very bad. It performs bad if you don't have many samples. In the extreme case, when you have less samples than the dimension, this thing you can see is low rank, right? Because you've got the dimension is p and the rank is n, and it's singular. And if you remember, in most of the examples I showed you, what you really need is actually the inverse covariance, not the covariance, so you can't even use it. And then people start talking about regularization, which we will mention. Another thing is that it is sensitive both to heavy tails and outliers. These are two different things, but we will deal with them together. It's easier to see it in the outlier case. Think about it, you've got one xi, which is very huge, equal to 1 million. It's going to dominate everything, and the sample covariance will just basically almost ignore the rest of the samples. And these are the two things we're going to talk about today. So what do people do in statistics for each of these problems? For the large p small n, let's first see why do we have large p small n. So I guess I don't need to explain. You guys work from vision. You have this problem much more than I do. But you've got this huge network, lots of sensors. On the other hand, and as we can go on, p always gets larger. And in many applications, n grows smaller every time because things become more mobile, more dynamic. You've got a shorter time where the samples really are relevant. And the classical thing to do, method to fight this is regularization. There are different philosophies who all lead to the same thing. You can call it bias-variance trade-off. Some people call it shrinkage, regularization. Some people come from a Bayesian philosophy. They put priors on it. All of them basically somehow try to regularize the solution or shrink it to something that we prefer from the beginning. So that was the high dimensionality. Now there's the other issue, right? The heavy tails and the outliers. Again, I don't think I need to convince you people that Gaussianity doesn't really hold in many examples. Outliers are also very common in many problems these days. The standard solution in statistics to this is robust statistics by Haber. And the ideas are usually, you can think about it instead of taking the Gaussian distribution, take a generalized version of it. For example, elliptical distributions are a bigger family of a class of distributions. Sometimes you just should take the likelihood and choose a more robust objective function. This is the classical example where you show the least squares, the quadratic objective versus Haber's objective function for standard regression, and you see that Haber's regression on the right doesn't take into account the two outliers because it's quadratic in the middle, but then becomes linear, and the outliers affect less. Okay, now our goal today is to have something which is both robust and regularized. Okay, because we want to fight both. So on the top you see the classical maximum likelihood. Then there are the two approaches, robust statistics, change the likelihood to some psi. Okay, you change the objective. And regularization. Regularization, you add some penalty, prior, shrinkage, whatever you want to call it. The second part of my talk today is about how we do both. We use both psi instead of the likelihood and add a penalty. And that's if I want to talk about the robust and regularized problem. Because I like optimization, so I like to think about things as problems. But some people prefer the solutions. So in this case, the solution to the maximum likelihood, as I told you, is the sample covariance. Okay, the classical robust sample covariance is some iterative scheme, which is a weighted sample covariance. Makes lots of sense. You put your weights, okay, that somehow measure how outlying is the I sample. Okay, and if you think it's an outlier, you weigh it down. But this depends on sigma, which you don't know, and that way it's an iterative scheme. Okay, so that's the solution. And some people, which I guess almost probably everybody here, probably use the covariance somewhere, and you usually like to add an alpha identity or something to it. You can call it ridge regression, you can call it Tikhonov, whatever you want. That's how you regularize the sample covariance. And again, what I'm going to show you right now is how I do both. How I put the psi, I use a weighted covariance, but that's still not enough. It's still low rank. We don't have enough samples. So I also add the regularization. So this, I think, was the long overview of what I'm going to talk about today. So I'm going to start by a simple idea. So one of the most common, has anyone here ever heard of Tyler's estimator or robust covariance estimation? So this is one of the most very, very common estimator. People use it all over in radar, and I don't know what. I'm sure that in machine learning somebody probably used it also. The idea is you take instead of using the Gaussian distribution, you go to a bigger class of distribution called elliptical. That's different names. They're almost the same, all of them. For us, they are. Some people call it spherically invariant Gaussian variable. Some people compound Gaussian. Some people call it scale Gaussian. Basically, it's all, instead of saying that X is Gaussian, but a multivariate Gaussian, a vector, you say it's a multivariate Gaussian times a scalar. Okay, now this scalar can be a random vector, a random scalar, or it can be deterministic, but you've got different ones for every I. Okay, and this leads to many of the distributions that all of you know. I think the easiest, in this context, the easiest way to think about, if you have outliers, so think about this ni will usually just be 1, 99% of the time. But once in a while, it's going to be a million, which is completely irrelevant. But usually you take different approach for heavy tails. But this is for this audience. If you do you write the maximum likelihood. You just write the distribution of this thing, you write the likelihood, you get this problem, this optimization. And this is a non-convex optimization problem. Now, convex optimization problem, this is convex, okay? This is not convex. In non-convex optimization problems, they're usually hard. You're not guaranteed when you go down, you usually know it, that you'll get to a local minima, okay? You're not necessarily going to find a global one. But already Tyler and then lots of people under different names did the same thing again and again, proved that although this is non-convex, they can't find its global solution. Okay, and it looks exactly like we said. It's a kind of weighted sample covariance, but adaptive. And the weights are they're on the right. They just check in using a standard distance, which comes from the optimization, how far X, how outlying is X.
So this is essentially the same as SVD. SVD is a non-convex problem. It's solvable.
That's exactly what I'm going to lead to it then.
The distribution of me?
Oh, okay. So there are different. Let's talk about this in there. There are different ways. If you, there are lots of ways to get from this depending on where you start. But basically, there are like a billion people did this. They all start with different assumptions. They get to this optimization, depending on whether it's random, deterministic, or something like that. But I'll talk to you on that. Okay. So first try this. So you need to understand this this estimator, which I will call Tyler or whatever, it works really well. Okay, and people use it all over, but it works very well only when you have lots of samples. Okay, it takes care of the outliers. It's good for heavy tails, but it's still only good asymptotically. That's all maximum likelihood estimators are. Now, already I think in '95, people realized that they need to use it in places where you don't have lots of samples. And they said, okay, let's add an alpha times identity like we do to the sample covariance. And now it will work. And it actually works very well. Okay, and people use it in radar and probably in other applications. And
So what is the psi? Is this a specific function?
yeah, the one I showed here. But there are so many papers on this, some of them with different sizes. This is the most general one.
But when you say P over, this is
P is the dimension.
scalar?
Yeah, it's a scalar. It's a scalar that weighs each sample. It's a weight for each of the samples. Okay, so this really works okay, and engineers did 5 iterations of it, and it works perfectly because they didn't try 6 or 7 iterations. Had they tried it, they would see that it diverges. And some of them did. They didn't show the results. Some did try to understand it.
In science, you never report failures.
Exactly. So there were a few who did report the failures. And they said, well, it does work, but let's add a normalization. Now, this normalization makes a lot of sense. Why does it make sense? Because, let's go back. Remember here, there is a scaling ambiguity in all of this problem. As I said, what are the needs here, right? I didn't say anything about them. And these are scalars. So we cannot ask, if we don't tell you anything about the NEI, you're never going to know the scaling. And it's true that these solutions are all optimal up to scaling. If you multiply sigma in all sides here by scala, nothing will change. Okay? So, and really, they said, okay, so let's just say that the trace is 1, doesn't matter. Some people normalize the determinant. And now, suddenly, it works perfect. So, actually, we did this. People did it before us. We also did it. And this is kind of state-of-the-art in radar these days. But, again, there's still no proof that it actually works. And it's kind of ugly. It's ugly. We kind of fixed it to work. So the first thing we'll do is prove to you that it does work always. So Tyler's iteration, the original one without regularization was non-convex, but him and under different conditions showed that it always converges to a unique limit no matter where you start. What we show in our work is that the regularized iteration with the normalization always converges to the same unique solution for any n, okay, even in the...
Good solution?
Thank you. I'm going to ask that in a second. It always converges, and it doesn't matter where you start. And this is like my teacher always told me, the first thing you need to show that it converges, then you need to show that it converges to a unique place no matter where you start, and then you need to show that it converges to a good place. So I'll skip the proof, but the proof is actually very cool. It's Perron Frobenius, but for matrices. Everybody here probably knows Perron Frobenius for vectors. So this is actually the fixed point here. It's just like Perron. We're actually converging to a maximal eigenmatrix of this iteration. Okay, so that was the first. We were very proud of it because we proved something that was open in many publications, something that people used all over and didn't exactly know whether it's always converging. So what did we have so far? We showed one type of regularization. We added the...
Just a question. Why do you care to prove something that everyone uses for so many years?
No, actually, we also used it. We also used it, and we wanted to prove that it converges and that it doesn't matter where you start, because otherwise every time you can get a different solution. So I think this is the first, like there are different levels of what you can expect.
Tali was kind of telling the difference between engineers and scientists, and I think that engineers shouldn't care
No, they should care. They should care. It's very bad if you have a system.
How many engineers?
It's a very...
all wrong, maybe all the bridges will fall tomorrow.
No. Engineers do care, and it's complete. You cannot build. You build cameras. You cannot build a camera that one day.
Because so you can know, you can start whenever you want, and you arrive to a solution. So
you cannot have. There are systems like that, but reliable systems, they should always yield the same solution with the same input.
The problem is that the class of problems that you can actually solve, prove things like this, is
small.
Extremely limited, I would say, sparse. Most of the things are not like this.
But that's what I do. I never claimed anything more. Okay, so that's so we did one type, and we regularized the solution. And as you asked, we don't really understand what we are solving. And the truth is, this estimator actually works very well. Now I know it converges and it's unique, but I have no idea what is it solving. And I didn't like this. And that's personal taste. And as I said, I also don't like the normalization, which most people don't care about. They say, who cares? Then I'm going to normalize it. I think it's ugly. And that's the second part. So what I'm going to do now is a unified framework that will have lots of regularization, different kinds. I'm going to regularize the problem rather than the solution. I'm going to give you guaranteed convergence. And I don't need normalization. And by the way, the original Tyler also didn't need normalization. Only the fix, only when you regularize it, you had this issue. Okay. So, how much time do I have more? I have 20 minutes?
Go ahead.
Okay. So,
200.
so as Tali kind of hinted, there's something good happening here. It's a rare case, it's very sparse, but there is something good here which probably people missed for many years. This is our optimization problem, okay? It's scale invariant. When you multiply it by a scalar, nothing changes. It's non-convex. Now I can show you. But when you start gradient descent, it always gets to the same place. So I had this feeling that there must be some kind of hidden convexity, hidden generalized convexity, quasi-convexity, superconvexity. Something good is happening here. And if we'll figure it out, then we'll know how to modify it. Okay, so that problem was very hard, and I said, okay, let's stop and let's look at a more simple problem. Let's forget huge covariance matrices. Let's look just at diagonal matrices, okay? Let's assume we know that the matrix, the covariance, that all the sensors are uncorrelated, but we're just estimating their variances, okay? So now we've got the same optimization as before, only now sigma is a diagonal matrix with sigma I. With a vector sigma, small sigma instead of the big sigma. Now this is still non-convex. But now, when people who do convex optimization look at this thing, they automatically see that there's a simple change of variables. If instead of sigma, which are all positive, we write in sigma I, we write e to the power of zi, we put it here, and suddenly we get a convex problem. This is a very nice convex problem. The beginning is the log sum x, which is a classical example in every course on convex optimization. And the log diag just becomes linear. Think about it, like you have this log sigma. This looks like this, it's not convex, right? But a change of variables to Ez makes it linear, right? And this is just a multi-dimensional version of it. Okay? So this thing is not, this is very easy, right? No wonder people solved it. And again, we just invented a new robust estimator, actually, of diagonal covariances, or just a robust estimator of variances, but which have the same outliers in all of them. We take this objective, we change variables, and now any simple descent method should do. And on the bottom here, you have an example. Here you've got an elliptical distribution, a multi-T distribution, that's chi-square times a large random vector. And you see our variance estimators versus the classical sample covariance, we are much better. And if the data is Gaussian, then we lose a bit because you don't really need all those iterations. But that's exactly the meaning of robust. Robust means that if the data is nominal, then you lose a bit in robust estimators. That's what you see here. But if the data has outliers, or in this case heavy tails, then you become much better. But so this was actually very nice, and maybe someday somebody might actually use it. But that was not our goal. Our goals was to go from scalars to matrices. So we would like to do the same thing with matrices. Now, like you, my first guess was, that's cool, we've got matrix exponentials, right? Let's take them out. If you take a symmetric matrix, there is something called a matrix exponential. If you apply it on a symmetric matrix, you get a positive definite matrix. Bingo, that's all we need. Doesn't work. No. No, but then it's not going to be positive definite. Yeah. But when I say positive definite, I also mean symmetric, because that's how you do it.
Exponents exist for every square meter.
Yeah, you're right. Okay, so this doesn't work. That's very cool, very nice. I checked it lots of times, it just doesn't work. You can do this change of variables, it doesn't convexify the problem. So we lost hope for a month, but then we went back to the diagonal case. What's going on here? And we said, okay, let's not do a change of variables. Let's work with sigma, but change the definition of convexity. And on the top here, you've got the definition of convexity. Convexity is a convex function. Take 2 points, push the line. The line is above the function, right? And the important thing here is the line is above the function. You can show that in the diagonal case, after playing it, you can show that instead of doing a change of variables, you can show that it's convex. But it's not convex on the line between the 2 points. It is convex on something else. On some path parameterized by t between these two. I call it a geodesic. It has something to do with shortest path, but it doesn't matter for now. The important thing is it's not the line between 2 points, it's another path, which is still parameterized by t. And on this path, you are convex. Now, classical convexity and geodesic convexity, or any path convexity, gives you almost the important stuff are the same. Local minima are global, and any descent algorithm will do. So now, the problem was that before I didn't know what was the change of variables that will make it convex. Now, instead of looking for a change of variables, all I need to do is, how do I generalize a line between scalars to a line between matrices? But this is something which is well known in signal processing and in manifolds. And this is a line. This is just a generalization of what we had before onto positive scalars. And when you plug this thing into the objective, you just need to show that it's convex on the parameter of the geodesic, this t. And this thing is convex on t, exactly like in the diagonal case. The beginning is a log sum x expression, and the second one is linear. Suddenly, it's no surprise that Tyler succeeded to solve it. Okay, he just did gradient descent on something which was convex. It was not convex in the regular definition of convex that we use, but it still has the same important property, that there's only one global only local minima.
This geodesic convexity was defined by this O5?
No. This guy actually didn't do this. I'll explain later.
Who did the geodesic convexity?
This thing I did. He did something on a different manifold, something without this. I'll explain it later. He did something. He actually, he did it on a different manifold.
So T here is what?
T is just when a line is defined by a parameter T. In 0, you are here. On 1, you're here. And
one row.
What? Yes.
It's one row. What is the meaning of T?
T is just parameterized as the line. Yes, that parameterized where you are on the segment. Okay? So now if you put here t equals 0, you're going to get sigma 0. If you put here t equals...
It's continuous connection between the
Yeah, between 0 and 1. And you want to show that you are convex on t.
So the manifold is the manifold of these two matrices?
Of positive definite matrices. But one of the important things here, I'm not using any manifold fancy stuff. And it doesn't really matter. Convexity, you need to find some path. Okay? The fact that this is the shortest path, this helps me guess what was the solution. But I don't need the shortest path. I'm not using the fact that it's a geodesic at all. All I need is if between 2 points you always have a path, and on this path you are convex, then any local minima is going to be global. That's the only important thing that I'm using. Okay, now it's kind of obvious what we need to do if we want to regularize our problem, right? We want to, well, this should be not L now, but psi. You take the robust likelihood, and you want to add a penalty to it, right? And what do you want? You want this penalty in order to guarantee that everything works okay. You want it to be geodesically convex. You want it to be scale invariant, so we wouldn't need a normalization. And you want it to promote whatever prior knowledge or structure you had on the problem, be it low rank, sparse, shrinkage to identity, and other things that I will show. And if I have that, then any gradient descent algorithm under technical conditions will find a global solution. So let me just give you a few examples that work. So this penalty is convex on the geodesic scale invariant, very easy to check. If you just try to minimize it, the solution would be any scaled identity. And therefore, when you add it to the likelihood, it will promote shrinkage to the identity. In some cases, and these are all the standard things that people do in regularization. In some places, you have some prior knowledge about from a different experiment about the data, and you know that sigma is going to be close to some positive definite metric. This is going to do the trick. Again, convex on the geodesic scale invariant. In many applications in genomics, they use it a lot. You want to do LDA, okay? Linear discriminant analysis uses the covariance, okay? You don't have enough, you use regularized linear discriminant analysis. It's very common that you don't want to shrink to the identity because different things have different scalings. Okay, so you want to just shrink to the best diagonal metric. Because, it's very similar, but it gives you more degrees of freedom. This, convex on the geodesics, scale invariant, and if you just solve this alone, you'd get any diagonal matrix. So when you add it to the likelihood, you get a solution that is getting you closer to the diagonal, which is more well-conditioned. Regularization of the condition number, also very successful in many problems in covariance estimation. This is like shrinkage to the identity, but just does it not in a linear manner, but in using thresholding. Kind of thresholds the upper and lower eigenvalues. But again, this function, we show it's convex on the geodesic and scale invariant. All you need to do is add it, and you get what you need. How do we minimize these functions? Who cares? Just use your favorite algorithm. This is an example just showing us. How many people here know Ledoit-Wolf estimator? Okay, this is like classic.
Not by this name.
Oh, okay. This is like the classical estimator for covariance regularization today. Used all over in finance, genomics. So that's the green. In the Gaussian case, it's very well. Does as good as the Oracle that knows everything. And our proposal is a bit worse. But when the data becomes suddenly non-Gaussian, Ledoit-Wolf gets much higher MSE, and we reach the Oracle. And here's a nice example for security. For you guys, this is not really the killer application, but just to show you that because I think these estimates, there's heavy tails and there's outliers. It's not the same thing, but our estimator, because of the weight, somehow deals with both. So this is more an outlier example. I'm sure you guys can find better ways with vision and fancy stuff to do this example better. But the idea is we put sensors in the corridor, people going in and out, put a webcam, we want to detect when someone enters. And we're going to use the simplest estimator, just an energy detector. Okay? It looks, we need the covariance to whiten the measurements, and then we use an energy detector. And depending on the estimator of the covariance that we're going to use, we get different performance. What you see here is detection rate versus false alarm. You want to get detection rate 1 with 0 false alarms. And different estimators give you different results. At the bottom, the blue, that's just using the sample covariance. Sample covariance, very bad. in black, you have a bit better. That's Tyler's estimator. That is a bit better. Because we have outliers here, we have people coming in and out also in the training set. So these affect the covariance, and that's why Tyler is a bit better than the sample, but there are not enough samples for Tyler to work. Then on the green, we've got the DOI-12, which is the today's state-of-the-art covariance estimation method for large p, small n, but that doesn't take into account outliers, and red is ours that does kind of both. And just as a sanity check, take this graph, and in the next slide, this graph is exactly what you saw before, but on the right, you have the same experiment, same data, only now we use supervised version, where in the training set, we took out all the outliers, and suddenly you see we're as good as DOI-12, because DOI-12 is very good in this scenario. And we've got lots of examples which learning people don't like to see MSE curves, so I will skip them. But as you can expect, we are always better under the right model. And discussion, so what did we show you? We started with the original estimator that with Tyler. Then people regularized it. Lots of people did. They didn't exactly understand why. They realized they had to normalize it. We proved that it works when you normalize it. Doesn't matter where you start. But we didn't like it because it's the solution rather than the problem. And it had this ugly normalization. And then we made a unified framework based on hidden duality, or hidden convexity. Which tools did we use? Concave Perron forbiddance, which is really cool. Convex optimization of manifolds. And the last thing is the graph. And that's it. What did you have? Yes, something. I remember I said I'll answer you. What? Okay. Depending on, knee can be random, and then you usually call it elliptical distribution with different kinds. And then what you need to do, you can, in this case, what you do is, to get that likelihood, what people did is, they didn't really use x, the measurement, but they used x divided by their norm, by the norm of x. The input to the algorithm is actually x divided by the norm of x. Each random vector, you first normalize it by its norm before you enter into the algorithm. And then this thing only depends on the Gaussian distribution, and it has some crazy distribution, which is exactly the log of what you've seen there. I don't know the name of this distribution. It's on this. And on the other hand, some people use compound Gaussian, or in vision, I think you call it scale. In image processing, use it scale Gaussian. They assume that knee is deterministic. And now you can take two ways. One way, you can just maximize over knee first, okay? And then use the concentrated likelihood. Because when you minimize, you can maximize first with respect to sigma or in knee. You start with knee, and then you get to the same thing. Or you can, from the beginning, normalize by the norm. And there's also spherically invariant, and they all lead to the same thing. And like many other variants of these things with different size, which all kinds of nonlinear functions of them.
All right, thank you. More questions?
So regularizing convexity implicit that you will converge, but what about rate of convergence?
Oh, well, I didn't even say how I solve it. That I leave to you. You will find the best.
A little bit about complexity. I mean, how does it scale with the definition?
Well, this.
Sample size or something. We want to know.
I'll let you guys study that. No, but
but your theorems, your proofs should tell you something about it.
Well, I didn't. You're saying how much should you regularize for a given?
I also had some sort of sample complexity bound. I mean, like how much data you need for certain accuracy.
Well, you will not get. I guess the answer. If usually you work in these things, you work in the asymptotic ratio, and then you don't need regularization, and then you know what's going on. When you start regularizing, all of these estimators, they don't get to the right solution. They are very, very much biased. These are regularized You don't know, and that's all I know how to say about it.
But you're trying to sell it as a way of dealing with large data.
Right.
So
How do people use it?
How large is large? I mean, how much?
I just don't know. I think it's very interesting, but I just don't know the answer. And people have been using these kind of things for 30 years all over. You do a ridge regression, you add some penalty, and it also depends on your goal. And I want to make it completely clear. These things will not work really to estimate each of the elements in the covariance. But if your real goal is not that, your real goal is just anomaly detection or an hypothesis testing, and this is a plugin, then people...
my goal is to have a good estimate of the spectrum of the mean.
Okay, so I'm saying, then you need to study, but then you need to study to take this plugin, put it in your problem, and for your problem you can get bounds. In general, this doesn't give you, it cannot give you.
Okay, so you really should plug it into another method which is using...
Of course. As it is impossible to estimate a huge P squared.
The covariance distance.
Also in the Frobenius distance. If you have small n, large P.
That's only like estimation of diameter. Anyway, so I hope we'll have some balance between very technical and very illuminating, whatever, combination of talks this morning. That the next session is really one of the best in the meeting. Don't miss it. We have coffee outside for everyone, and again, I'm up in mind is we have lunch for everyone here. לא בטוח שאני לא מסתבר לך. זה נראה מהפרטים של הפרעה. Inspiring.